Good evening. This presentation will discuss the development of a method that is non-invasive to record neural activity. A paper, which is referenced at the end, is followed very closely, highlighting the scientific question of why its development is necessary, how its emergence has tackled such concern, and the current limitations it is facing. It should be noted that the paper is not fully covered in this presentation, rather a summary of it. Referring back to the original paper, therefore, it is very advised for a better understanding. With that stated, here are the contents of the presentation in which they will be discussed in a chronological order. So to start off, an introduction to neurological biocomponent would be applicable. So what exactly is neurological biocomponents? Well, in the past few years, engineering and medicine has continued to grow in the fields of bionics, which is transforming therapeutic approaches for many indications. Through the exploitation of neural bionic devices, it has now become possible to electronically substitute damaged nerves or neurons to overcome failed information processing. Although these advances were initially focused on stimulation technologies, the field has also greatly impacted the development of devices that restore human senses, such as hearing and sight. Nowadays, advances in chronic neural recording devices have enabled control of robotic prosthetic limbs for the treatment of paralysis and have improved seizure prediction with chronic telemetry in refractory epilepsy. Intracranial electrode arrays such as penetrating cortical microelectrodes and subdural electrode arrays have enabled neural recording and decoding for complex motor prosthesis and epilepsy seizure monitoring. It may then follow that if a successful approach is already in place, why is there a need to develop another one? Well, although penetrating cortical arrays have achieved the highest spatial resolution for neural recordings, they are invasive, may cause trauma to brain tissue during insertion, and may result in chronic inflammation, gliosis, and disruption of the blood-brain barrier. In addition to that, existing cortical implant design and implantation procedures are associated with difficulty in accessing deep cortical regions, such as within sulcal folds, which may be information-rich regions. Therefore, there is a need for interfaces with improved biocompatibility, high-resolution signal transduction, and long-term functionality that can be implanted with minimal trauma. In the paper, the authors demonstrate the feasibility of chronically recording brain activity from within a vein using a passive stent electrode recording array, or for short, Stentrode. Spectral content and bandwidth of vascular electrocartography were comparable to those of recordings from epidural surface arrays. Cerebral veins naturally lie in sulcal folds and may represent an avenue to deliver minimally invasive cortical interfaces. The clinical utility for an endovascular recording system depends on its ability to achieve long-term recordings in awake and mobile subjects. Long-term deposition of electrodes inside a vein to achieve stimulation and/or recording of local neural tissue has been reported previously in the form of the implantable artificial cardiac pacemaker and defibrillator. Intracranial stenting of cerebral blood vessels is an established technique in endovascular neurosurgery for the treatment of both arterial and venous neurological conditions. But the capability to record endovascular electrophysiological activity for extended periods of time has not been reported scientifically previously. Here the authors report a chronically implantable endovascular device capable of recording intracranial neural activity. The authors assessed human cortical veins with respect to their proximity to potential recording sites in sulci and developed a large animal model to target the sensory motor cortex. Furthermore, the authors demonstrate the ability of a self-expanding stentrode delivered by a catheter angiography to record vascular electrocardiography in awake sheep for up to 190 days. The authors validated the electrophysiological signals captured with the stentrode by comparing them with those obtained from electrode arrays implanted via craniotomy. Moving on to the mapping of cerebral veins and cortical surface. To assess the suitability of human cerebral veins as an implant target to record vascular electrocardiography, the authors have focused on feasibility studies on the sensory motor cortex. The authors specifically focused on the central sulcus. As previous work demonstrated, the anterior bank of the motor area is information-rich for motor decoding when compared with other areas of motor cortex. The authors characterized the venous anatomy surrounding the sensory motor cortex using brain magnetic resonance imaging, or MRI for short, data from 50 patients as shown in the figure. Let's deviate a bit from the discussion and discuss the findings in this figure, as it will come in handy later on in the discussion. The figure displays superficial cortical venous variability in humans and sheep model. Looking at part A in the figure, three-dimensional reconstruction of human pile surface, motor cortex, specifically Brodmann area 4, highlighted in red, and sensory cortex, specifically Brodmann area 1, which is highlighted in yellow, with co-registered superior sagittal sinus and central sulcal vein, which will be discussed later on. Dotted lines represent segments of vessels characterized at 5 millimeters increments, where the scale bar is 3 centimeters. Part B highlights the incremental diameters and distances of the superior sagittal sinus, commencing proximally at post-central sulcus, defined as 0 millimeters at this instant, to the nearest Brodmann area 4 and area 1, when the number of samples is 50. In part C, similar values for human central sulcal vein, commencing at the superior sagittal sinus with the number of samples being 50. Part E illustrates sheep's superior sagittal sinus's diameters and distance to motor area over 13 samples. Lastly, Part D showcases three-dimensional reconstruction of sheep's superior sagittal sinuses and motor cortex, highlighted in red, and its sensory cortex, highlighted in yellow, where the scale bar is 1 centimeter. Now, going back to the discussion after detailing crucial parameters of the figure shown, following the characterization of the venous anatomy surrounding the sensory motor cortex using MRI, a network of 4 venous structures lying in the sulci in close proximity to sensory motor cortex are identified. Those are superior sagittal sinus, or SSS for short, which were covered earlier, precentral sulcal vein, or pre-CSV for short, central sulcal vein, or CSV for short, and fourth, post-central sulcal vein, or post-CSV for short. The central sulcal vein was closest to the cortical surface, lying immediately adjacent to the motor area, i.e. Brodmann area 4, at a point along the vein 25 millimeters distal from the convergence with the superior sagittal sinus as being shown in the figure. At this point, the CSV, or the central sulcal vein, had a diameter of 3.7 millimeters along 48 samples. The vein then continued distally, immediately alongside the motor area for a length of 70 millimeters, reducing in size along the course of the vessel to 2.3 millimeters. Superficial cortical veins displayed some minor anatomical variability in the proximal segments, reflected by reduced concordance of repeated inter-observer and intra-observer measurements of vessel diameters. Now, why is this analysis being drawn between humans and sheep? Well, to find a suitable animal model, the authors assessed superior sagittal sinus size and position in sheep as a comparable vessel to the human central sulcal vein using MRI scans of sheep brains. Sheep's superior sagittal sinus lay adjacent to motor cortex and displayed comparable vessel diameters and proximity to cortical surface. Because the internal luminal diameter of the sheep's superior sagittal sinus was 2.4 millimeters proximally, reducing to 1 millimeter distally, the authors considered it an appropriate venous structure in which to perform validation experiments. Now, looking at the main tool used to record neural recordings, the authors built their stentroids on intracranial stent technology, currently in clinical use, to facilitate easy transfer from animal models to humans. A commercially available self-expanding stent is used as a scaffold for the attachment of 750 micrometers diameter laser-cut platinum disc electrodes, as shown in the figure. To maintain the superelastic properties of the nitinol stent, the authors mounted electrodes along the repeating stent strut, cross lengths to 2.5 millimeters. The self-expanding scaffold enabled the electrode arrays to be compressed during minimally invasive delivery by a catheter and to achieve nonlinear expansion to match target vessel curvature for closed vessel wall opposition of electrodes against cortical surfaces after deployment. To achieve distal access of our stentrode to vessels equal in size to human cortical veins in the sheep model, the authors used an angiography-based coaxial catheter technique, effective at delivering a A4 catheter to the sheep target vessel with a diameter of 2 millimeters. Catheterization of the cerebral venous system was challenged by irregular venous anatomy, including valves, chordae, and arachnoid granulations, to which this obstacle was overcome with specific catheter over wire techniques. The stentrodes are implanted into the superior sagittal sinus immediately adjacent to the motor area. By suturing the lead at the common jugular vein puncture site in the neck, the authors achieved hemostasis tunneled subcutaneously to a custom-made hermetic connector secured to the sternocleidomastoid and exited the skin by a flexible percutaneous lead, which terminated in a microcircular plug. In conclusion, the paper highlights the development of an intracranial stentrode array deployed via minimally invasive catheter angiography in a cerebral vein to achieve chronic recordings in a freely moving sheep for up to 190 days. Early incorporation of the stentrode into the vessel wall was associated with an improvement in recording sensitivity. An endovascular neural interface does not require craniotomy for implantation and may facilitate access to superficial as well as deep brain targets. The sheep's angiography model used the network of superficial veins and sinuses that lie adjacent to areas of cortical surface with blood vessel internal lumen diameters of 1.2 to 3.2 millimeters. The authors report the use of a delivery method that can deploy a stentrode in vessels as small as 1.7 millimeters. Although the veins in the human brain were focused on as potential translational target in superficial cortex, the arterial system may also provide an avenue to targeting deep brain structures. Deep structures including the nucleus accumbens and subgenual white matter are known to lie immediately adjacent to the anterior cerebral artery with a diameter of 1.9 to 2.6 millimeters. Other structures not currently targetable with craniotomy, which may be accessible via deep arteries in the human brain, include the subthalamic nucleus, hippocampus, and internal capsule. A stentrode that provides intracranial recordings with spatial resolution and spectral content similar to that of an epidural array may facilitate a range of clinical applications. The ideal location of sinuses and cerebral veins overlaying superficial cortex may make them natural targets for placement of passive endovascular sensors in a brain-machine interface or epilepsy telemetry recording system. Avoiding direct contact with cortical neurons may mitigate brain trauma and chronic local inflammation, but this requires additional evaluation. A stentrode delivery to a venous sinus may be the safest initial target in humans, owing to the established technical precedents in the form of transverse sinus stenting. However, the paper proposes that the cortical veins are higher yield targets with greater exposure to cortical surface and no dural layer that may cause signal attenuation. There are mainly two limitations to this developed approach. The first is durability of the delivery wire, the second being the density of electrodes. So tackling the first one, a current limitation of this prototype technology is the durability of the delivery wire for the stentrode. The device was built on Stentrode technology that was not designed for chronic implantation, and wire fatigue associated with repetitive neck movement was observed. Future approaches may borrow from solutions used for cardiac pacemakers, where the issue of chronic repetitive wire fatigue has been overcome. A potentially safer alternative would involve a wireless signal and power transmission system, but currently available technology remains too large for safe endovascular deposition. Going on to the second limitation is the density of the electrodes. The achievable density of recording electrodes might be increased with the removal of wires, the use of a smaller electrodes, or with custom designed stent technology would be far more suitable. Further investigation is required to determine the maximum electrode sensitivity and spatial resolution with a stentrode incorporated in the blood vessel. An endovascular neural interface offers a method for safe, reliable, and chronic neural recordings. Just as interventional cardiology progressed into electrophysiological applications after the demonstration of the long-term safety of electrode deposition in veins, which has led to major therapeutic advances that included artificial cardiac pacemakers, the authors also envisage that future applications of endovascular arrays may include motor cortex sensors in brain-machine interfaces and seizure prediction in epilepsy. Applications in neural simulation open the possibility of achieving deep and superficial brain stimulation therapies without the requirement for craniotomy. Multiple deep brain stimulation targets have been identified as being accessible via arteries and veins, with targets for Parkinson's disease and obsessive compulsive disorder being particularly suitable. Thank you.